Welcome students. So we are going to discuss about series solutions to a ordinary linear differential equation of second order at a regular point. So let's start with our differential equation px y double prime plus qx y prime plus rx y equals to 0. So now it has regular point at x equals to x0 if what we get is limit as x goes to 0 x times qx divided by px and limit as x goes to 0 x square rx over px. These limits are finite. One, and we have, and these functions are analytic at, so these functions are analytic at x0 and x qx over px and x square rx over px are analytic at x equals to 0. Yeah, recall what the analytic means that is they have convergent power series. Power series at 0. Now note that if this is not x0, if x0 is not 0, if x0 is not 0, say x0 equals to a and a is not 0, then substitute x0 minus a, yeah, and that will be 0, right? So this is the idea. So now once we do this, we have, notice that we have y double prime. If I divide throughout by px plus px of y prime plus qx y equals to 0, where px is, I'm calling this as px, where px is qx over capital P of x and qx is capital Rx over. Now to start with, generally these px and qx are basically any analytic function, but we can take px, qx and rx to be polynomials. We don't have to restrict ourselves to the polynomial. Now we'll rearrange this ODE to look like an Euler equation. So we can make it look like Euler equation. Recall, how did Euler equation look like? Euler equation was x y double prime plus px x pxy plus qxy equals to 0. So this is what your Euler's equation was. So we'll make this equation look like an Euler's equation. Which equation? This equation as an Euler's equation. So we divide throughout by, so we get px y double prime plus qx y prime plus rx y equals to 0. So divide throughout by px, so we get y double prime plus qx divided by px y prime. Now we get rx divided by px y equals to 0. Now call this as p. So this is equal to px. Call the other one, call this as q. Qx, therefore we have y double prime plus p of x y prime plus qx y equals to 0. Now if you multiply throughout by, so we want to make it look like this equation, right? So what we'll do is we'll multiply throughout by x squared. So we have x squared y double prime plus x times x px y prime plus x squared times qx y equals to 0. Now you can see why our definition of regular point is the way it is, right? So you see we need limit as x of qx by px and x squared by rx by px to be finite. So now and to be analytic. So we need that they are finite and they are analytic. So this is what we need. So let's see. So what do we get out of this? So the upshot is, so here we get the following. Now from above, we are guaranteed, from above, we are guaranteed that what xpx and x squared qx have convergent power series. So now that means we have x squared y double prime plus x. Now instead of writing this guy, I'll write down the convergent power series, which is going to be p0 plus p1x p2x squared. These are the coefficients, dot dot dot, plus q0 plus q1x dot 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 y prime here, y here equals to 0. Okay. Right. So now if we get Pn now note the few details here, namely the following, that if you look at this guy, limit as x goes to 0 of x px is going to be p naught, and limit as x goes to 0 of x squared qx, which is basically finding the limit as x goes to 0 of this, which is going to be q naught. Now if Pn equals to Qn equals to 0 for all n not equal to 0, then let's call this equation star, then star reduces to x squared y double prime plus x p naught y prime plus q naught y equals to 0, which is an Euler equation, right? Which is an Euler equation, and we have already seen this, C 5.4. Now, however, so let's move on to discuss about the format of the solution. So now we are interested in this power series here, sorry, this differential equation, and we want to solve this. Let's discuss the format of the solution. Now, in this case, for the sake of simplicity, we'll take x to be greater than 0, because if x is less than 0, for simplicity, and x is less than 0 can be dealt in same way. Same way, but what you have to do is you have to define a new variable t equals to minus x. Yep, this method was used in the earlier 5.4. Okay. So now, so our differential equation. So how does our solution looks like? So we have, first of all, our dE. dE is of form x square y double prime plus x p naught 1 plus p1 by p naught x dot 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 p y prime plus q naught 1 plus q naught q1 by q naught x dot 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 y equals to 0. Note that here p naught is not equal to 0, q naught is not 0. So now what do we get? So we seek a solution. So we seek a solution of form y equals to x to the r a naught plus a1x, which is x to the r summation n equals to 0 to infinity a n x to the n, which is summation n equals to 0 to infinity a n x to the power n plus r. Now, why are we seeking solution of this format? So please note that if this x square term was not there, so suppose if this x square and x term was not there, we would have, and these term, this was already analytic, then we had to use we'll get the usual power series analytic. We'll only need to use this part here to get to the solution, because then we get an ordinary point. However, because of existence of this x square and xpx, we'll have to take a solution of form x to the r times this. This is to take care of the singularity. Okay. So now we need to find, so what do we need to find? First of all, we need to find r, and second, a n for all n. So these are the two things we need to find when we need to find out the solution. So note here that r need not be an integer, r need not be a positive integer. So we define basically to approach such problem, we define a special kind of series called Frobenius series. So what is the Frobenius series? So you take basically summation n equals to 0 to infinity a n x to the power r plus n is called Frobenius series. where R belongs to R is fixed real number. Yeah, so in some sense it's a generalization of power series. All right, there are different ways to generalize the power series, and this is one of them. So one, every solution, every differential equation of form Px y double prime plus Qx y prime plus Rx y equals to 0 with a regular singular point. Yeah, this is the important part. You need regular singular point. Point at x equals to 0 has at least one solution. One solution that is a Frobenius series. Yeah, so clearly, so another note of caution here that since R is not necessarily an integer, Frobenius series is not a power series. It's not a power series. So now how do derivatives look like? So derivatives look like in the following. We get y prime x is going to be summation. If you take derivative of this, you get summation n equals to 0 to infinity an r plus n to the power times x to the power r plus n minus 1, and y double prime is going to be summation n equals to 0 to infinity an r plus n times r plus n minus 1 times x to the power r plus n minus 2. Okay, so now let's work on finding a solution. So find the exponents in the possible Frobenius solution of the equation following 2x squared plus. So first of all, convert it into a standard form. So convert into form y double prime plus pxy prime minus plus qxy equals to 0. So how would we do that? We'll divide throughout by dividing by 2x squared. So we get what? We get y double prime plus 3x 1 plus x cube y prime upon 2x squared into 1 plus x minus 1 minus x squared divided by 2x squared 1 plus x y equals to 0. Now we need to check. So is x equals to 0 a regular point? Is a regular singular point? So now if you convert this into, we can write this as plus 3 by 2 times 1 plus x square by x y prime minus half 1 minus x by x square y equals to 0. So now, before I apply any of these, so any of the techniques, I need to check that. And for that, notice the following: limit as x goes to 0 of x px. So this is your px. So this is equal to px, and this is equal to your qx. Limit of x goes to 0 of x px is 3 by 2 times 1 plus x square, which is going to be 3 by 2, which is finite, right? And similarly, limit as x goes to 0 of x square qx is going to be, so 1, if I multiply it by x square, I'll be left with x goes to 0 minus half 1 minus x, and x goes to 0, I get finite. And these are analytic as well. What are analytic? These guys are analytic. So we have, these are analytic as well. Okay. So now that we have that they're analytic, we basically get to this part. So we have the following star as a differential equation. So now let's write down, multiply throughout by x square and write down the corresponding Euler's equation. We have x y double prime plus x times, so we have what? We have so we get this thing here. So our, when I write down the corresponding Euler equation, I get xy double prime plus 3 by 2 x times p0 plus p1x y prime plus q0 plus q1x y equals to 0. So then from here you can get basically an identical solution. So you get basically x square. So we get x square y double prime plus 3 by 2 x p naught. So we get 3 by 2 x y prime minus half y equals to 0. Yeah. So now if we substitute, if we substitute x to the r in this equation, we get x times x to the r would give me r into r minus 1 plus, here we'll get x to the power r minus 2 plus 3 by 2 times x into r into x to the r minus 1 minus half x to the r equals to 0. Now, if we take x is greater than 0, so take x square out, x to the r out, so this will combine to give you x to the r. This will combine to give you x to the r. So if we take x to the r out and divide it throughout, so since x is greater than 0, we have r into r minus 1 plus 3 by 2r minus half r equals to 0, and this gives me r square plus half r minus half equals to 0, and this in particular implies r into r square, so 2r square plus r minus 1 equals to 0, and when I factorize it I get r minus equals to minus 1. So I get, when I factorize this, I get r plus 1 times r 2r minus 1 equals to 0. So therefore r equals to minus 1, or r equals to 1 over 2. Therefore there are two possible Frobenius series solutions. Namely of form y1x equals to x to the half summation n equals to 0 to infinity an x to the power n, and y2 equals to x to the power minus 1 summation n equals to 0 to infinity bn x to the n. Now note that here, while we were trying to find out, so this equation is called, this equation has a special name. It's not a characteristic equation, but it's called Indical equation. So, Indical equation. So strategy is straightforward. What you do is you first find the Indical solution, and that gives you how will the corresponding Frobenius solution look like. Okay. So so here, from here to here, there's a jump, but you can see that you can directly write it down. Since P naught and Q naught, you can, using P naught and Q naught, you can find out what your if I write this inside, so I have 3 by 2 here. So if I write it, I can write this series as x times 3 by 2 plus 3 by 2 p1x and so on. So I right away get p naught. However, the another way to see the p naught is you get p naught here, and similarly your q naught is here. So the idea is when you get p naught and q naught, you can directly write down the corresponding Euler equation, and then you can go ahead to find the Indical solution. Now this can be all done more formally, namely the following. You can put the power series in and try to solve for it. So what do I mean by that? So another way to find out the Indical solution in this case is the following. So what I'll do is we will write down y of x. So another way to find, not another way really, another way to find Indical solution. I shouldn't call it another way because it's essentially the same way. I mean, you are here, you're just reading the what will happen. And so let's basically take y of x, which is going to be summation n equals to 0 to infinity a n x to the power r plus n, the Frobenius series solution, and sub it in this equation here. So we get what? We get 2x squared times 2x squared times 1 plus x, 1 plus x. Now what y double prime is what? Summation n equals to 0 to infinity a n x to the power. So the second derivative of this is going to be r plus n times r plus n minus 1 times x to the power r plus n minus 2. Then we get plus 3x times 1 plus x cube divided by, 1 plus x cube times y prime, which is going to be summation n equals to 0 to infinity a n r plus n times x to the power r plus n minus 1 minus 1 minus x squared times summation n equals to 0 to infinity a n x to the power r plus n equals to 0. And then you basically then solve for r from here. Yeah, so such method is going to be tedious. However, you can quickly jump from, once you find P naught and Q naught, you can quickly jump to the corresponding Euler equation as we did here. Okay, and the answer would be the same. So let's look at the following. So find the series solution to the following equation. So we have y double prime 2xy double prime plus 3xy prime minus x squared plus 1 equals to 0. The first step, divide throughout by x squared, divide by 2x squared. This gives me y double prime plus 3 by 2 y prime by x plus 1 by x squared plus, so divide by x squared, so it's going to be 1 plus x squared divided by x squared times y equals to 0. Now, note that limit as x goes to 0, and so this is my px, right? So this thing is equal to px this is equal to qx. This part is px, and this is equal to, so I can write this as plus minus, so this is equal to my qx. Note that limit as x goes to x times px is your 3/2 px is this part here. Yeah, without the y prime part. X times this is 3/2, which is your p naught. Okay. And similarly, limit as x goes to 2 of x square qx is limit as x goes to 0 x squared times minus 1/2 1 plus x squared by x squared, which is going to be minus 1/2, which is your q naught. Are finite, and x px and x squared qx are analytic. 0, therefore we have x0 equals to 0 is a regular singular point. Step 3, find indical equation. So to find indical equation, we have the following. So what we'll do is consider x square y double prime plus p naught y prime x y prime plus q naught y equals to 0. So that is, we get x square y double prime plus 3/2 x y prime plus minus half y equals to 0. Now to find indical equation, sub x to the r equals to y, therefore we get what we get on both sides. We get y double prime is going to be x squared times r into r minus 1 times x to the power r minus 2 plus 3/2 times x into r x to the power r minus 1 minus half x to the r equals to 0. Now x is not 0, so this implies r into r minus 1 plus 3/2 r minus half equals to 0. And you can directly write from here to here. This is your indical equation. Now we need to solve for r. So this gives us, simplify, you get, if you simplify, you get r square minus r plus 3/2 r minus half 0. This implies r square minus plus 1/2 r minus 1/2 equals to 0. We need 2r square plus r minus 1 equals to 0. This gives me, when I factorize it, I get 2r minus 1 times r plus 1 equals to 0. So therefore we get r1 equals to half and r2 equals to minus half. So this is our solution to the indical equation. So very similar to the theory of a homogeneous second order linear differential equation with constant coefficients, right? There you had characteristic equation, you have indical equation here. So then Step 3, form solutions. So form solutions of form y1 equals to x to the half summation n equals to 0 to infinity a n x to the power n, and y2 equals to x to the power minus half summation n equals to 0 to infinity bn x to the n. So fourth step, use y equals to x to the r summation n equals to 0 to infinity cn x to the power n to do both the cases above, cases y1, y2 at once, and then solve for, then later put r equals to half or r equals to -1. So we want to do this in generality now. So substitute, so 4, 5, substitute in DE. We have what, when we substitute this in DE, what do we get? We get, substitute this in the original DE, we'll see in this one here, we get 2 summation n equals to 0 to infinity n plus r n plus r minus 1 cn x to the power n plus r plus 3 summation n equals to 0 to infinity n plus r cn x to the power n plus r minus summation n equals to 0 to infinity cn x to the power n plus r plus 2 minus summation n equals to 0 to infinity cn x to the power n plus r equals to 0. So you can see that I've substituted in this equation here. Okay. Now what do we get? We shift the indices to make exponents same. So shift indices. To make exponents equal. So what are the exponents we need to make equal? So here we have x to the power n plus r. Here we have x to the power n plus r. We have n r plus 2. So we have to shift this indices, right? And rest everything work out. So we will have 5. So we'll get 2 summation n equals to 0 to infinity n plus r n plus r minus 1 cn x to the n plus r plus 3 summation n equals to 0 to infinity n plus r cn x to the n plus r minus summation n equals to, now I'll start this with 2 cn x to the power n plus r minus 2, so n plus r minus summation n equals to 0 to infinity cn x to the n plus r equals to 0. Now we'll compare the coefficients. So So now we'll treat two cases separately. Because of this, we'll treat n equals to 0 and n equals to 1 separately. So however, n equals to 0 yields 2r times r minus 1 plus 3r minus 1 times c0 equals to 2r square, which becomes 2r square plus half r minus half c0 equals to 0. Now this shouldn't be surprising. This part should be similar to the identical equation, right? Because in identical equation we take a shortcut to find this, but so n equals to 1 gives us 2r into, sorry, instead of r I'll have r plus 1, so 2r plus 1 times r plus 3 times r plus 1 minus 1. So it's similar as the above equation, and which basically gives me 2r squared plus 5r plus 2, c1 equals to 0. So this is true for both, for both. So this is true for both r equals to half and r equals to minus 1. So that would basically force that, since we get c1 equals to, so we have that when you put r equals to half and r equals to minus 1, this equation will get what? Something non-zero times c1 is 0 for both of them. So this implies c1 is 0 for both cases, both when r equals to half or r equals to minus 1. So now we need to look for the coefficient of x to the r. X to the power n plus r, and equate it, so we'll get 2. So let's see, let's compare. So what equation? So we'll get this plus this plus this minus this equals to 0, right? So we get 2 n plus r minus 1 cn plus 3n plus r cn minus 2 minus cn equals to 0. So now from here I'll solve for cn based on the previous terms. So that's what the idea is, to write the recursion. So we get solve for cn. So when you solve for cn, we get cn equals to cn minus 2 upon 2n plus r square plus n plus r minus 1, and n is greater than or equal to 2, because for 0 and 1 we have already done that case. So now we'll take two cases. So 8 7, sorry, separate the two cases. What two cases we have? Cn equals to an when r equals to half, when r equals to half, Cn equals to an when r equals to half, and we get c0 equals to a0, and we get Cn equals to bn when r equals to minus 1 and c1 equals to 0 equals to a1. So next, so let's deal with these two cases now. So case r equals to half case, we get an equals to an minus 2 divided by 2n square plus 3n. So when you simplify, you'll see that that's the case. And why is that? Because we have 2. Let's look at the denominator. We have n plus half minus 1 is going to be 2n square plus n plus 1 by 4 plus n plus half minus 1, which simplifies to, if you can see that there's a cancellation going to happen, except we'll be left with 2n square, n, 2n plus this will become 3n, and 1 by 4, 2 times 1 by 4 and minus half, that will become basically 0. So thus we get what? Thus an equals to 0 when n is odd. So we have an equals to 0 when n is odd, and when n is even. Why is it an equals to 0 when n is odd? Why is that? Because we found out that C1 was 0 in both the cases. So your C1 is your A1, and that is 0. And that would imply that A3, which is related to your A1 upon 2 times 3 square plus 3 times 3 is also going to be 0, and consequently A5 is going to be 0, so on. So an is 0 when n is odd. Now, when n is even, we have, say, we have A2 equals to, so now let's put A2 here. So A2 will be A0 divided by 2 times 2 square plus 3 times 2, which is going to be 8 plus 6, so 14. Similarly, A4 is going to be A2 over 44, which is going to be A0 over 616, and so on and so forth. And A6 is going to be A4 over 9t, which is going to be A0, 5, 5, 4, 4, 1, 0. So what do we get? We get y1 x. Either you write A0 out and x to the half, because x to the r, what is the solution here? The solution is x to the r summation n equals to 0 to infinity an x to the n. So the odd ones are out. What you're left with is even ones, summation k equals to 0 to infinity. So I want to write down all the even ones now. So a to the power 2k x to the power 2k, actually a0 is not there, and then this can be written as a0 x to the half. Let me write down the few terms. So we have x squared plus 14 plus x to the 4 by 616, x to the 6 by 55440, and so on. Now the question is, can we find out a closed form? And the answer is yes. The closed form is here already. Yeah, just that the previous one is getting multiplied with this 2n squared plus 3 all the time. Yeah, so we write it in this format. Now similarly, let's deal with the case when r equals to -1 case. In that case, we are having, what is our solution? Solution is a form y x to the r summation n equals to 0 to infinity bn x to the n. We also have b1 equals to 0. So this implies bn equals to 0 for all odd n. Now, what is Bn minus 2? Again, the same way. It's the same thing as Cn, right? But instead we have R equals to now -1. So Bn2 is going to be Bn minus 2 upon 2n squared minus 3n. So check. B2 is going to be B0 by 2. B4 is going to be B2 by 20, which is going to be B0 by 40. B6 is going to be B0 by 2160. And hence the solution is a form y2x equals to B0 x to the power minus 1, 1 plus x squared by 2, x to the 4 by 40, x to the power 6 by 2160, and dot dot dot. All right, so let's come back to the following differential equation. So find a solution to the Bezel's equation of order 0. Now, this kind of differential equations are very interesting because, say, for example, if you look at this one, here, these kind of differential equations are important in wave propagation, studying wave propagation. And here we have alpha is what? Alpha is 0. So let's first write it in the standard form. So step, write in standard form. So divide by y double prime. So divide by x square, which will give me 1 by x y prime plus y equals to 0. We have px equals to 1, qx equals to x square. And here, since we can see limit as px is 1 over x, and qx is x squared by x squared, which is 1. So limit as x goes to 0 of x px equals to 0, and limit as x goes to 0 of x squared qx is equal to 0. So this is 1, my bad, and this is 0. So since these are finite, therefore what do we have? 0 is a regular singular point. If it is not a regular singular point, we can't do what we are doing here, namely finding the power C expansion. So this is called P naught, and this is called Q naught. So now we want to basically have corresponding, so we want to basically solve, so indical equation. So in this case, the indical equation is going to be here, r squared plus P naught. So we get r into r minus 1, sorry, for the first part, plus P naught times r plus Q naught equals to 0. So this is how the indical equation works. So we get, in this case, we have Q naught is 0. So we have r into r minus 1 plus r equals to 0, which means r squared equals to 0, which gives me r equals to 0 is a single exponent. So therefore, we get Frobenius series solution is y of x summation n equals to 0 to infinity Cn x to the power n. So let's work it out. So we get y double prime. So y prime is summation n equals to 0 to infinity Cn x to the power n minus 1 times n, and y double prime is going to be summation n equals to 0 to infinity n into n minus 1 times Cn into x to the power n minus 2. So therefore substitute. So this was step 1 in some sense to do write in standard form. Indical solution is step 2. So indical equation. Step 3 is basically writing down the Frobenius series solution. So this is step 3. Substitute in given differential equation. So we get what? We get, if you substitute in this differential equation, you will get summation n equals to 0 to infinity n into n minus 1 times x to the power n minus 2 x squared out. Then we have xy plus x times summation n equals to 0 to infinity n into x to the power n minus 1. So, and then we have x squared plus x squared times summation n equals to 0 to infinity n x to the power n equals to 0. So now we basically organize them together. So we have what? We'll shift the indices. So we have summation n equals to 0 to infinity n into n minus 1 x to the power n plus, so here we have Cn, summation n equals to 0 to infinity Cn times n x to the power n minus 1 plus summation n equals to 0 to infinity Cn x to the power n plus 2 equals to 0. Now we can combine these two guys, and this one we have to shift an indices. So if you shift the indices, you'll get summation n equals to 0 to infinity n in square minus n plus n times Cn x to the n. Plus here, now I'm going to start with n equals to 2. So starting with n equals to 2, what do I get? Cn minus 2 x to the power n equals to plus, what else do I have? I have C0 from the first one. So we get this equals to 0. So n equals to 0, n equals to 1. So n equals to 0 gives us no information. N equals to 1 implies C1 is 0. And now for n greater than equal to 2, we have, if you look at this part here, this is going to be, so we have n square C1. We have n square Cn equals to Cn minus 2 with a minus sign. This implies Cn equals to minus Cn minus 2 on n squared. Now again, since C1 is 0, so C1 equals to 0 implies Cn equals to 0 for all odd n. So now we get C2 equals to minus 1 plus C0 by 2 squared. we get C4 equals to minus C2 by 4 square, which is going to be C0 by 2 square, 4 square. So if we observe this pattern, or let's look at C6, which is going to be C0 with a minus sign, 2 square, 4 square, 6 square. We have C of 2n is going to be, first of all, minus sign is alternating, right? So minus 1 to the power n. If you take out 2 here, if you take out 2 from here, so you get 2 times 1, 2 square times. So we get 2 to the power 2n times n factorial square. So depending on your, so this is what you have. This is your solution. Okay, why is that? Because this is same as, notice that this is same as minus 1 to the power n C0 over 2 square, 4 square, 6 square, dot, 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 2n square, right? If you take, this is minus 1 to the power n C0, if you take 2 square common from each, all of them, you get 2 to the power 2n, and what is left in the bracket? 1 square, 2 square, 3 square, 1 square, 2 square, 3 square, n square, and that can be written as n factorial square. So we get, this implies, so if you take C0 equals to 1, special case, we get solution to be minus 1 to the power n, x to the power 2n, 2 to the power 2n times n factorial square, summation n equals to 0 to infinity. And this is a very well-known function. It's called, this is the Bezel function. Okay. Right. Thank you for your attention.